Last time we were talking about uses of different gases for cutting and welding, and I showed that the 230 degree higher 80 bag flame temperature made oxyacetylene flames 36% more useful in terms of providing heat for welding of steel than MAP gas, which is C3H4 rather than C2H2. So the people that say acetylene is better, if they're talking about welding, that's true. We also mentioned that oxyacetylene cutting, we started getting into the cutting process and how the cutting eliminates the boundary layer. Essentially the gas that you're blowing in there is the, would ordinarily be the boundary layer, but in this case the oxygen is reacting with the iron and condensing to form a liquid oxide. And so there is no gas boundary layer. You're essentially creating a vacuum, if you will, at that spot. And I put mostly down because in a few minutes I'm going to show you where there is some contamination and how that contamination actually does produce a partial boundary layer, which slows down the process. Iron is the fuel in oxy-fuel cutting. It really doesn't matter whether you use MAP gas or propane or gasoline. People actually use gasoline sometimes for oxy-fuel cutting. It's not going to limit the productivity because the time that it takes to initiate the cutting process, where you're using the oxy-fuel flame to start the cut, typically takes 10 or 15 seconds. And if the whole cut's taking several minutes, it really doesn't matter if it takes 10 seconds or 12 seconds. You know, 2 seconds out of several minutes of cutting time is really not going to make a difference significantly in productivity. There are distinct safety advantages and handling advantages when you go to something other than acetylene. We talked last time about how acetylene can't be stored under extreme pressure, and that means that it has to be stored dissolved in acetone. That makes the tanks heavy. Either that or you have to have calcium carbide around, you drip water on it inside a big tank and pipe it around the facility. But in terms of safety, that creates the problem that acetylene is one of the most flammable gases we have. Its flammability limits are like 3% to 80% concentration in air. So it doesn't take very much acetylene to reach an explosive limit, or there's a very wide range of explosive limits, so that if you get an acetylene leak, you have a high probability of a dangerous situation. In fact, one of the things people should learn is what to do in case of a fault in an acetylene cylinder. There was a case in the problem in western Massachusetts where a plumber had a little spare time with his workmen, so he went and had him, he was going to put in a new bathroom in the basement of his house. So he went and got one of his workmen set up in his house. He had a little B cylinder of acetylene, and the guy got him set up, said, "I'll go out and get some lunch," and he left about 11 o'clock, and he came back about noon with the lunch, and the house was on fire, and his plumber was out in the yard. And he ended up, it was kind of interesting because the guy ended up suing himself in order to get things back, because he was the homeowner, but he also was the owner of the plumbing company, which is also under his own name. So he was suing his own company for burning down his house. That has to be insurance companies involved. His homeowner's insurance was different than his company insurance, but nonetheless, what had happened is there was a brand new B cylinder, and there was a machining defect on the valve seat where the valve is supposed to come down and close against this resilient gasket material, supposed to close against the valve seat, except there was a little cutout in the valve seat. And so the first time the guy cracked the valve, there started to be this leak, and the cylinder caught on fire, and there's a little flame coming off the cylinder, and he tried to blow it out, but you know, the gas just keeps on coming out. And actually, one of the worst things you can do is to blow it out, because if you blow it out and all you're going to do is fill up the basement with this explosive mixture, which is going to go find a pilot light over the gas furnace or something and blow up the house. The guy would have found it just a big hole when he got back to his home, rather than a partially burned down house. So the the plumber, not knowing exactly what to do, just ran out of the house and left the thing burning, and it burned down the house. Well, does anybody know what you should have done in a case like that? You can't blow it out. You take it outside with you and you let it burn outside. And you're supposed to hose it down to cool it off. You don't want the cylinder itself to get hot enough that it could explode because the contents are going to go hydrostatic and blow the thing. So you're supposed to just, you don't try to put the flame out, because if you put the flame out, you're just letting gases accumulate somewhere that could go off explosively. You basically try to just keep the container cool so it doesn't blow up itself, and let the thing essentially extinguish itself by burning out all the flames. But it is sort of dramatic. Actually, if you want, I don't know when we do it, but I have a videotape from the Compressed Gas Association that actually shows a safety videotape, acetylene tank with a leak in the top, and it's just a great big flamethrower, about 6-10 feet tall, just a great big flame shooting up. You know, I had a high school physics teacher who we used to be able to convince them every now and then to turn on the gas jets and light them, you know, on the chemistry benches, you know, and you have a flame shooting out that far. That was worse than my passing around the torches in here.
Did that video win any awards?
No, it didn't win any awards. Although it's sort of actually the one there's one part of it. There are fusible plugs. Fusible plug is just a low melting metal that if the tank gets hot, the fusible plug will melt and release the pressure. So it's just another safety device, and these things are required by the Department of Transportation on these things. But just to show what could happen if someone were to defeat a fusible plug, the Compressed Gas Association video actually shows what happens when you take an acetylene tank and they put it in the middle of a big valley about the size of a football field, and they have this video from some distance away, and they've defeated a fusible plug, and they essentially ignite the whole cylinder. And you just see a fireball fill up the whole football field. The whole valley just turns into a great big fireball when it ignites. If you want, I can bring that in. You might want to clap at it. It's sort of fun. But the cylinder, basically a fuel gas cylinder, is a big bomb so far as that goes, if you know how to ignite it. Fortunately, there are lots of safety devices to prevent that. But because acetylene has high flammability limits, because it's heavy, if you're going to dissolve it in acetone, you've got all this weight of this liquid acetone. It's easier to deal with liquid hydrocarbons, or hydrocarbons that can be liquefied under pressure, such as propane and MAP, and don't have these problems with higher pressures. And so they're more convenient to use. Down in my own lab, we actually have an oxyacetylene setup, and we have an oxy-MAP setup. We use the oxyacetylene for welding, use an oxy-fuel for welding, and we use the MAP for cutting. It's just the simplest, easiest way, safest way to do it. Other questions? With regard to what slows down the cutting process, in your handouts you've got a paper from 1955 called The Iron Oxygen Combustion Process by A. Wells. Dr. Wells later went on to become the Director General of the British Welding Institute, but he was actually I guess he still is, an excellent scientist, although he's retired. He did a lot of work in fracture mechanics and essentially invented the COD specimen, if anybody's familiar with that in fracture mechanics. But in this particular article, he basically looked at what the effect on the relative combustion rate for oxyacetylene cutting is versus the oxygen purity, or the equivalent, what he called the equivalent oxygen purity of different steels with different carbon content. You're burning the iron, and iron oxide is a liquid condensed phase, but steel is a mixture of not just iron, but iron and carbon. And if you burn carbon, you're going to get CO, or CO2, mostly CO. And CO is not a condensed phase. So in fact, you would create your own boundary layer with carbon monoxide gas. The oxygen condenses to form FeO, but some of the oxygen doesn't condense, it forms carbon monoxide, and you have to blow that away. The higher the what this shows is the higher the carbon content of the steel, which means coming down this direction, the slower the relative combustion rate. And very low carbon steel, actually Armco iron, which is virtually pure iron with no, they call it Armco iron because it's not really a steel. There's virtually no carbon in it. You can cut at 1.5 times the speed of low carbon steel, which they kind of gave a unit combustion rate here. Swedish ingot iron is up here. Free cutting steel, which is in medium carbon steels. You get to razor steels, which have more than 1% carbon in them. And you find that they cut at about 1/2 the speed as a regular low carbon structural steel. Fortunately, we're usually cutting structural steel, so we don't lose that 50% in productivity. You can also, he called this equivalent oxygen purity. You can also add impurities like nitrogen to your oxygen, and if you're at 99%, you can get fairly high cutting rates. But as you drop down to 90%, you put 10% nitrogen in the oxygen, and you'll drop your cutting speed down by about half. In fact, he showed in his paper that 1% carbon had the same effect as 6.2% nitrogen, if you want to know precisely what that means. That means that you have to have reasonably pure oxygen. Now, it doesn't really matter whether you're 99.5 or whether you're 99.0, that's not a big difference on that scale, but it does make a difference whether you're 95% or whether you're 99%. I was once at a welding show, which has won some awards, so far as that goes anyway, but only from other welders. But in any case, welding show is where all the people display their wares. And this was a number of years ago. Someone was using zeolites to essentially produce oxygen out of air. Ordinarily, to produce oxygen out of air, we use what's called the Lindy process, the Lindy division of union carbide. Lindy was some German scientist 80, 90 years ago who figured out how to liquefy air relatively economically. If you liquefy the air, you can then distill it, basically, and you can separate it out into oxygen and nitrogen. And that's still the way we produce liquid oxygen, liquid nitrogen, and get relatively pure oxygen and nitrogen. And in any case, that oxygen is 99.99% oxygen. It's very, very pure in the distillation process of liquid air. But another technique that these people were using was to use zeolites. Zeolites are little ceramic particles that have a very well-defined open crystal structure. And if you get the right type of zeolite, you can design it so these little open structures will absorb certain types of gases. And a nitrogen molecule is a different size, slightly, than an oxygen molecule. And you can change the charge inside these little cavities if you change the chemistry just right. And so you can have a preferential absorption on these internal surfaces of these zeolites. And so you basically just take an air compressor, take a tank full of zeolites, you pump it up to 1,000 psi or something like that, and let the air preferentially, or let the oxygen preferentially absorb on these zeolites in preference to the nitrogen. You close the valve, turn the compressor off, and or you blow off the nitrogen gas, and you have this oxygen that's stored in these zeolites. You open up another valve, reduce the pressure, and the oxygen comes off the zeolites. And so you have a source of relatively pure oxygen, relatively pure being 95%. That's a heck of a lot better than you start out at 20%. Now, this turns out to be not a very economical process. Liquefying air is less energy intensive, but this is something that you could kind of have your own portable thing. And if they're not gonna, the people trying to sell this didn't tell you about your electrical cost of running a compressor, but assuming that electricity was free, this would be a very good process, they thought. So I was walking through and they asked me, they were trying to sell me this, and I went up just to see what it was, and they found out who I was, and they said, well, so what do you think? Figuring they had some professor from some well-known school, well-known in some circles anyway, depends on where you go. And I said, well, it wouldn't be very good for cutting, which is what they were trying to sell it for. And they said, why? I said, because 5% impurity is going to lower your cutting productivity by about 25-30%. And well, that wasn't what they wanted to hear. So, but in fact, it is true. And in fact, the bigger problem was the economic cost of the electricity to run the compressor. If you want to have liquid oxygen, the easiest thing is just to purchase it. Either that, or if liquid nitrogen is free, you can manufacture your own liquid oxygen. I used to do this when I was a grad student, because I used to have to do 1 year as a TA. I was in charge of the 3091 demonstrations. And one of the demonstrations that we used to do was to describe paramagnetism and diamagnetism. Anybody remember what those are? No one remembers? You know what ferromagnetism is? Ferromagnetism is a big, strong, permanent magnet, right? Well, diamagnetism was where you have an equal number of spin up and spin down charges, spins on the electrons. And paramagnetism comes when you have an unequal number of spin ups and spin downs on the electrons. And it turns out oxygen is paramagnetic and nitrogen is diamagnetic. Or wait a second, have I got that backward? No, that's right. Oxygen is paramagnetic. And if you go through and look and see the 2s shells and 2p shells and count up all the electrons and stuff, you can prove to yourself that one of them completely cancels the positive and negative, or up and down spins, and the other one has an excess spin. So one of the things you can do is you can take this big, strong ferromagnet, which we had in the lab, and it had about a 1-inch gap, and if you try to pour liquid nitrogen into the gap between that magnetic field, it will actually be repelled by the strong magnetic field, because, if I remember, it's diamagnetic. And so if you try to pour it straight down, when it sees the magnetic field, it just sloshes over on either side. But if you pour liquid oxygen in there, it turns out it will be levitated in between the two coils. The other thing about liquid oxygen, it has this beautiful blue color. Liquid nitrogen is white, clear, but liquid oxygen is just beautiful blue. So you can make liquid oxygen from liquid nitrogen by just taking a little copper coil and putting it down in a tank of liquid nitrogen and running some oxygen gas through it, because liquid oxygen condenses at a higher temperature than liquid nitrogen. So liquid nitrogen will condense the liquid oxygen. So I used to make a few ounces of liquid oxygen and pour it in between the magnet pole pieces. I doubt that the safety office knew we were playing around with pure liquid oxygen in the lecture halls in 10250, but nonetheless, if you do it quickly, there's a lot of other oxygen in the air. Has anyone ever seen the Purdue University barbecue lighting contest? If you go to Purdue University and you look on their website, I found it once. They actually had a contest each spring at spring barbecues of who could light the charcoal fastest. And they would have different things. And the winning thing that kind of stopped the thing forever, they have someone with like a 10-foot pole pouring some liquid oxygen on some charcoal, and you see poof, all the charcoal turns to ashes in seconds. Okay, the potential pressure, thermodynamic pressure of liquid oxygen is thousands and thousands of atmospheres of oxygen, and the kinetics, of having that much oxygen that close to something that like carbon that can burn is quite impressive. Okay, liquid oxygen doesn't explode, but it can burn other fuels at a speed that is essentially explosive. So it's not to be toyed with. If you want, where will you find lots of liquid oxygen? Where do you go from time to time? Probably not more than once a year at your age. From time to time, there's hospitals. They're full. They have liquid oxygen pumped all the way through the walls. Okay. Unfortunately, they've got a lot of safety precautions, and they don't blow up hospitals that often. However, some people do blow up things with liquid oxygen. I wanted to do another little aside before I get into arcs. Well, actually, with the other little aside, I ought to do. Which one do I want to do first? Well, let's talk a little bit about cutting first. And I didn't do some overheads on this. I did show you a jet burner the other day, and it turns out oxyacetylene cutting has been the cutting process for carbon steels for 80 years. But in the last 10 to 15 years, for cutting ordinary thickness steels, and that means up to about 1 or 2 inches, plasma cutting has displaced it for primarily environmental and productivity reasons. And essentially, plasma cutting is a process that is essentially an arc burner instead of a flame. It's an arc burner, arc jet burner. And remember, a jet burner was something where I mixed the oxygen and the fuel and I combusted it inside the chamber at constant volume. And so all the PDV work of the heating of the gas caused it to shoot out at very high velocity. And we talked about using oxyacetylene jet burners to drill through rock and things like that. Well, it turns out that a guy named Bob Gage at Union Carbide's Indianapolis Speedway, or not Indianapolis Speedway, but Indianapolis Laboratories, across from the Indianapolis Speedway. And I read you the story of how Fisher and Allison had developed all that. In the mid-1950s, was studying tungsten arcs. And he was studying gas tungsten arcs for welding, because Union Carbide sold a lot of gases for welding. And he was doing basic research on gas tungsten arcs. Well, a gas tungsten arc is nothing more than a tungsten electrode that you strike an arc. Okay, W is tungsten, right, for Wolfram. So this is the regular gas tungsten arc, where you just have an electric arc and a base plate down here. And Bob was trying different types of gases. He was trying xenon and argon and neon and helium and trying to figure out what would happen in these arcs. But one of the things he decided to do is he decided to drill a hole in the base plate. This was a water-cooled copper plate, and he drilled a hole, and I remember talking to him about why he did it, and he didn't remember exactly why he did it, but he was trying to see what would happen for some reason. And he ran the arc over this, and he had a flame shoot out the backside through here. This was basically plasma. You have, we're going to talk later when we get to arcs, about how you have fluid flow in the arc, and that fluid momentum with a hole here, instead of going off to the side, created a flame of hot ionized gas. Now here, the flame is not due to a chemical reaction, it's due to electricity. And we'll talk about that when we get to arcs a little later this morning, or tomorrow. Well, it turns out from that little observation, Union Carbide in the late 50s invented the plasma arc welding process, where you have a tungsten electrode and you have a water-cooled copper shell, and you basically strike an arc inside a chamber at constant volume, and you have a gas jet, on this case, an ionized gas, which originally was argon, but people have learned to use other things, like rather than tungsten, they now use hafnium as the electrode, which is also a refractory metal. The nice thing about, well, the reason they use hafnium is they actually find they can use air as the gas through here, whereas if you use tungsten, anybody know what would happen if you struck an arc with tungsten arc in air? Tungsten actually forms an oxide, tungsten trioxide, WO3, which is volatile at about 1500 centigrade. And that, the tip of that electrode is like 2500, 2800 degrees centigrade. And so you would get a white smoke, which would be tungsten oxide, and your electrode is just burning away, which is not what you want. It turns out hafnium forms a refractory oxide, HFO2, which also has a slight electrical conductivity. And so it turns out you can get a hafnium electrode that even when it oxidizes will still carry enough current that you can basically use oxygen as your shielding gas. So now we have what we call plasma cutters, and instead of a oxyacetylene flame, we essentially have a very rapid gas jet, compressed air jet, which is heated by a plasma flame up here in this constant volume chamber, and shoots out at very high velocity. And I can melt through. If you remember all those other things I said you couldn't oxyacetylene cut stainless steel. You couldn't oxyacetylene cut aluminum or magnesium. Essentially the only things you can really that are common materials. You can't do nickel. The common materials are tungsten, or low carbon steels, medium carbon steels, low alloy steels, and titanium. And I think I passed around a piece of titanium last time, which has a fairly ragged cut. And if you flame cut titanium with pure oxygen, it works. There's the proof of it, but it also produces copious smoke and fumes. In fact, one time we used to cut thick titanium in the weld lab downstairs all the time being every couple of months. And one of the support staff across the hall would complain that they see some smoke coming out of the lab, and we had blowers down there and stuff. So one time they called up the safety office. This was the old safety office 20 years ago. The new safety office probably would have had me in handcuffs and taken me up to Cambridge Police, but the old safety office comes over to hear about this complaint, and they knock on the door, and they come in the weld lab. I wasn't there, and they ask my technician, says, the guy sees all the smoke in the lab, and he says, what are you doing in here? He says, I'm oxyacetylene cutting titanium. And the guy says, what kind of lab is this? He says, it's a weld lab. And the safety officer says, well, what do they expect to come out of a weld lab? Except smoke, right? Nowadays, like I said, they probably have me in handcuffs and taking me away. But it turns out TiO2 is not really toxic. It may be objectionable, but it's not toxic. In any case, in plasma cutting has kind of taken over because it has a productivity advantage, it has a quality of cut advantage, and it can cut other materials. This is a piece of half-inch stainless steel, which I'll pass around. It's been plasma cut. In this case, there's no chemical reaction generating heat. You don't have to, there is a boundary layer, but you're basically punching through the whole thing, so you're sweeping part of the boundary layer away. And you just melt through the whole thing with just total thermal energy. You can't cut 24-inch thick like you can with oxyacetylene, where you're burning through the material and using the material itself as its own ignition source. Here you're just melting through. Now this is just a simple square, and you'll notice where they start and where they turn corners, they don't get nice square corners, and that's because I have a thermal pattern that I'm carrying along, and when I turn the corner I lose the symmetry of that thermal pattern, and that creates some bad corners, which is still a problem for plasma cutting. That's in stainless steel. This is actually a laser oxygen cut in stainless steel to compare it with. That was someone looking, a medical instrument company looking to make a cheaper way to make scissors rather than forging them. Here is a laser cut on a piece of sheet metal so this is laser with an oxygen assist, piece of sheet metal, and they started in the center and cut out a circle. Probably the largest application for metalworking lasers right now is in cutting of sheet blanks. Now you don't have to, in the old days when you're stamping out parts out of sheet, you had to actually make tooling, which was very expensive, and every shape you wanted to cut, a new set of tooling for $40,000 or $100,000 or whatever. With laser cutting, you can do one-of-a-kind parts. You put it in the computer, put it on a little NC table, and you make beautiful cuts, beautiful surfaces. That's oxygen cutting. These two are basically plasma cuts. You'll notice on this one, the reason I brought this actually is an oxyacetylene wrench for an oxyacetylene tank. Just cut out a piece of steel plate. But if you look through this, you'll see a slight tapering to the holes because I'm not burning through, I'm just melting through, and so there's a slight tapered edge to the plasma cut surface. But you can see that the edges have a beautiful cut to them. This one is just a complex shape they did for testing. You can see here where they started in the center, cut that hole, and the rest of it's just cutting things to show you. But you can also see the tapered edges on that one. So those are some other cut edges. Well, they have to be conductive. Well, it turns out, we're jumping ahead a little bit. If you remember, an arc will give you 10,000 watts per square centimeter. Okay, and a flame, oxyacetylene flame, will give you about 1,000 watts per square centimeter. So this is a gas tungsten arc burning at constant pressure. This is a gas tungsten arc burning at constant volume. And this is going to have a higher volume. This one is just free expansion at 1 atmosphere pressure. This one is no expansion. It's constrained and it's expanding out this one little hole, which gives it a higher velocity. The velocity here is going to be on the order of 100 to 500 meters per second. The velocity here can be supersonic, but it can be, let's just put in a number, 2,000 meters per second. It depends on the size of the hole and everything else. But it can be a substantially higher velocity. And the velocity over here may also be 50 to 100 meters per second, almost as fast, but you don't have as much heat here. The temperature here is around 10,000 Kelvin. The temperature here is 3,000 Kelvin. And so lower velocity, this is actually 100 to 500 typically. Lower velocities, lower temperature, lower heat intensity across that boundary layer than you get over here. Well, this is higher velocities, not substantially higher temperatures. If that's 10,000, this might be 12,000. Okay, it doesn't go up a whole lot. Nonetheless, it's going to give you something on the order of 20,000 watts per square centimeter. Okay, so if I want to move up watts per square centimeter, I can move in this direction. Oxy-fuel plasma, 1 atmosphere, and plasma burning at constant volume. This is called the plasma arc process, invented by Union Carbide. This was invented, well, actually I don't know who invented it, but it started being used commercially during World War II to weld aluminum. Because oxyacetylene has all kinds of problems with aluminum. Aluminum likes to react with the gases and form oxides and things like that. This was a much cleaner process. The U.S. Navy and the Philadelphia Navy shipyard was building aircraft. There wasn't an Air Force back then. And during World War II, they were building aluminum structures. They were gas tungsten arc welding them. So this process really came in the 1940s. This was invented about 10 to 12 years later at Union Carbide because Bob Gage put a hole in the plate to see what would happen. In any case, you'll get higher heat intensities, but not a whole lot higher. So now the question, what was your question again, Chris? It has to be conductive. It turns out tomorrow we're going to get to the fact that 90% of the heat in this process is carried by the electrons to the surface. So you ground, I'll call it ground, but it turns out, yeah, this is a negative ground in this case, okay? It's the negative electrode. You ground this surface. Here, this would be a negative potential. This would be a positive potential, but in order to get the 20,000 watts per square centimeter, you have to ground this. And so this is positive, this is negative, but this is more negative, okay, electrically. So I actually carry current through here, and this is called the transferred arc process. And so yes, the workpiece does have to be conductive. It turns out that if I were to run this process and not carry current through here, I would get about 2,000 watts per square centimeter, not 20,000. Why? Because 90% of the heat in the arc process is carried by the electrons, only 10% by the hot gases. I have hotter gases and higher velocities here than I have over in this process, but if I'm not carrying the current, it's only a doubling of the oxy-fuel process. It's not a doubling of the arc process unless I carry current here. So it turns out there's what we call transferred arc plasma processing, where you have to have a conductive substrate because you're carrying 100 amps or 200 amps of current through here. And there's non-transferred arc plasma processing, which has 10 times lower heat intensity, but you don't have to have a conductive workpiece. You can use a piece of ceramic. So if you want, you could use a non-transferred plasma arc to do your hole drilling in rock. Except it'd be a very, very expensive thing that you're putting down the borehole and you tear it up very quickly. But we can talk about some of that stuff a little bit later. So in any case, plasma arc cutting, because it produces less smoke. In fact, one of the advantages of plasma arc cutting is if you're going to a shop that's bringing in lots of plate and then doing lots of fabrication down there through the rest of the shop, they actually will have their cutting process and they will do it underwater. The plasma arc can be run underwater, so it's a smokeless process. Whereas over here, oxyacetylene cutting, there's a fair amount of smoke. There's a lot more if you're doing titanium than iron, but that's when the safety office gets called by the staff here. But there's a fair amount of smoke, and so for environmental reasons, for quality of cut, for speed, plasma arc cutting is taking over, particularly in shop environments. It's also taking over in the field because you have these new power supplies. In fact, we could bring one up, I guess, tomorrow. It's a little compact power supply. It's about the size of a big briefcase and weighs about 50 or 60 pounds. You plug it in 110 volt power, you have some compressed air, and I can cut any piece of metal around that's no thicker than 3/8 of an inch thick and cut it very quickly. So if anybody wants to go around and play around with that. So it's very cheap, very fast way to cut steel, and even a little more expensive for the capital equipment, but the increased productivity makes up for that in the long run very quickly. So plasma arc cutting is replacing a lot of oxyacetylene cutting. It'll never replace it all. Both processes have their niche in different applications, which actually gets me to the topic, the other digression, which will take the last part of today. It turns out, before I get into arcs, I'm going to get into arcs. The oxyacetylene process took off right around the turn of the last century. 1910 was when they started having large quantities of acetylene available after this guy in North Carolina learned how to make calcium carbide cheaply. And calcium carbide, you just dump the water on and it produces acetylene. So now if you want to have something exciting at a party, you go get some calcium carbide from lab supplies and throw it in someone's swimming pool and light a match, right? And everybody will be surprised to see the water go on fire, right? In any case, it turns out that the first arc welding, I think I mentioned before, was, well, the first electric arc was Sir Humphrey Davy in like 1807, but no one had a power supply. It wasn't until Edison and Westinghouse came along in the 1870s and 1880s, and one of them was pushing DC power and one of them was pushing AC power. Which was which? Anybody remember? Edison was DC, and he lost for good reasons, okay? It's not like the VCR and Betamax, where Betamax was a better technology, or Macintosh versus PC, where Macintosh is a better technology. The one that won here was the right one. The right one was AC technology because you could use transformers to step up and step down the voltage, whereas DC, you didn't have great ways to do that. Now it turns out, anybody know what company Edison founded? It's a big company, General Electric. Where did he found it? No, Lynn, Massachusetts. Right on the Lynn River Works of General Electric. They still build jet engines there. And he founded it with, he had 700 US patents. The next largest patent holder ever was a guy named Elihu Thompson, who had like 400 or 600 or something. He was just behind Edison. The two of them were the founders of General Electric. What was Elihu Thompson's original job? He was a professor of electrical engineering here at MIT. He was, for 1 year, the acting president of MIT. In fact, there's an Elihu Thompson professorship over in electrical engineering. But in any case, General Electric was founded by Elihu Thompson and Thomas Edison right up the road here in Lynn, Massachusetts. In any case, when they started producing generators to generate electrical power, all of a sudden people started having large quantities of electrical power, meaning 10 to 20 kilowatts, available to do arc welding. The problem with arc welding at the time is people would just take a steel wire. I mean, you could take a coat hanger, so far as that goes, except a lot of coat hangers today are aluminum, but the old coat hangers, nice rusty ones, were steel, lacquered steel. You could take a coat hanger and you could weld something. Well, the problem if you do that is you end up with Swiss cheese, because iron and nitrogen don't like each other, in the sense that liquid iron will dissolve a lot of nitrogen in the air, but when it solidifies, it rejects the nitrogen, because solid iron doesn't like nitrogen. It rejects the nitrogen, you end up with Swiss cheese for a weld. So in the 1880s, people were doing arc welding, but only when they wanted to stick something together. It was the Scotch tape of the day for steel, if you get down to it, okay? But it wasn't a high-quality joint. If they wanted a high-quality joint, they would still rivet things together back in the 1880s and 1890s and 1910. And then two things happened, or the same thing happened in a slightly different variation in two different parts of the world. In Göteborg, Sweden, a welder who was welding with a steel electrode learned that if he stuck the electrode in the mud and welded with a muddy electrode, the weld no longer had these holes in it. It was not Swiss cheese. It was a solid weld deposit. And that is the predecessor of what's now called the ESAB company today, which is one of the world's largest manufacturers of what we call stick electrodes, or manual metal arc electrodes, or the official name is shielded metal arc electrodes. Steel wire, where nowadays they extrude a proprietary coating. These proprietary coatings have all kinds of different things in them, but basically this is a mineral coating. This is a 7018, one of the most popular high-strength, low-hydrogen electrodes. They essentially extrude it in a continuous process. They have a continuous wire of steel that pushes through, and they extrude, like coming out of a toothpaste tube, this cement-like coating on the outside, which they later dry in an oven. They brush this end so that you have something to make electrical contact to start. They brush a lot of the stuff about an inch off here so that you can grab it with these little copper tongs to make your electrical connection, and you can weld with this. Some of the highest quality weld deposits we make in steel today are still made with this type of electrode. Very cheap or very inexpensive to use. That's a stick electrode. Meanwhile, in the United States, and I don't know who it was or where, but someone in the United States was welding with these bare electrodes, and they found that if you wrapped a piece of paper around the electrode, the porosity went away. And this is called a cellulosic electrode. This is what's called a 6011, a little bit lower strength than that. Operates, its ability to control the puddle and operate the puddle is outstanding, okay, in some of these cellulosic electrodes. So it's easier to learn on these. That makes a higher quality weld deposit. And in fact, that 7018, you have to have the most skill to operate. But it's not a tremendous amount of skill. These comes in all kinds of different sizes. Again, they clean off one end so you can grab it. They brush off the other end. The cellulosic electrode, basically, you're decomposing the cellulose powder. That electrode over there is contained a bunch of minerals: calcium oxide, titanium dioxide, aluminum oxide, manganese dioxide, or manganese oxide. Inside, what they call a water glass binder. Water glass is basically a sodium silicate, which is a glue. It's used in all kinds of things. Cheap dishwashing detergents. It's used in postage stamps, or used to be, as an adhesive. But it's used as an adhesive to bind the cement together. Cellulosic electrodes use a sodium silicate as well as the binder, but they use different types of cellulose. Old wood chips. Turns out one company likes to use old tobacco stalks. And the reason is tobacco concentrates the rubidium from the soil. You probably didn't know your soil had rubidium, did you? Okay. But tobacco stalks will actually concentrate the rubidium. And it turns out rubidium, being lower down in the first column of the periodic table, is an arc stabilizer. So, and what else are you going to do with old tobacco stalks, right? If you burn them nowadays, people are going to tell you have to do it outdoors and you can't do it in a restaurant, and you know, all kinds of things. So everybody's got a proprietary formulation for these things. but they're basically commodities around the world. They come in a number of different sizes. Here's one of the largest. Okay, this is 36-inch, 5/8. They call it 5/8 inch diameter because that's the steel rod size. Now this one, the ones I passed around, probably 100, 125 amp units, depending on their diameter and stuff. This one is about a 2,000 amp unit, and this one a human cannot operate. Basically, this one gets clamped into a machine, and it's made by the Weld Mold Corporation. And if you go into a steel plant where they have big ingots, they make big ingots of steel or other metals, and these ingots might have 10-inch thick walls, and so it's a great big piece of cast iron with 10-inch thick walls. Those things crack sometimes, and so they have some guy go in there with an oxyacetylene torch. He gouges out, cuts out a big space in between, and they set this up with a machine, and they just crank in a couple of thousand amps, and they just melt metal, okay? And they make a new piece of cast iron, or they weld the two pieces of cast iron with lots of energy. So anyway, most people haven't seen them this big. I actually only own 2 of them myself, and I've never run one. I have seen them run. It's pretty dramatic. It's kind of hard to believe they're actually making a weld. It's more like they were just blowing electrical energy all over everywhere. So that's, okay, so let me finish up that, because one person was a little somewhat interested in the history. So between 1910 or so, when these stick electrodes first came out, all of a sudden, what happened next? What was the big event between 1910 and 1920 in the world? World War I, right? And there was a professor at Harvard who actually became, for a period between 1914 and 1917, a professor at MIT, named Comfort Avery Adams. And Comfort Adams had graduated from Case Western Reserve University as an electrical engineer. And this was not too long after Edison and Westinghouse. Electrical engineering was coming into its own, and people were developing new types of transformers and electrical equipment and stuff. And so this professor at Harvard, Comfort Avery Adams, was a professor of electrical engineering, and he was working on these types of transformers and stuff, and he was developing in his research welding power supplies. Can you imagine today a professor at Harvard designing welding power supplies? But anyway, 100 years ago, that's what he was doing, because it was cutting-edge technology. During World War I, he was made head of the Emergency Fleet Committee of the U.S. government, because if you remember, there was a song, over there, oh, the Yanks are coming in. Well, they had to get them over there. They couldn't take them over on a 747 back then. They had to take them over in ships. And they had to take several million of these doughboys across the ocean, and they didn't have enough ships. And so they had to start building ships on a crash basis. And so they had a committee, and Comfort Adams was head of this committee. And back then, they were riveting ships. If you went and looked at Commodore Dewey's battleships at the Battle of Manila Bay or whatever, they were all riveted battle cruisers. And back then, you couldn't rivet more than about an inch or 2 thick. But they wanted to weld, and so they tried to weld, but they didn't have the best electrodes, but they did weld anyway. Now, turns out between 1914 and 1970, Comfort Adams was also a professor at MIT. Anybody know why? 3 times from 1865 until 1917, Harvard tried to buy MIT. MIT was over in Copley Square. They were landlocked. They didn't have any space to grow. And President Eliot of Harvard wanted to purchase MIT. Finally, they tried 3 times. The alumni voted it down. Finally, it turns out that the Supreme Court of Massachusetts said they couldn't use the Gordon McKay Trust Funds. I just got an announcement this morning about a professor at Harvard who's giving a lecture. He's the Gordon McKay professor at Harvard. And Harvard's School of Engineering and Applied Sciences is the Gordon McKay School. Gordon McKay was a shoe merchant in Boston who gave $10 million to Harvard in like 1900 and 1910. $10 million that back then would be like 200 or 250 million today. This is a big donation. And and it also turns out Andrew Carnegie and some other people gave some money for Harvard to buy some land right across from where Harvard Square is, right across the river, so they could build their new engineering school. And they were trying to purchase MIT, and they wanted them to merge. And I may bring in, if I can find it tomorrow, Thomas Edison's quote about MIT at that period of time. But in any case, they wanted to merge, but one, the MIT faculty voted it down, or as I say, MIT'd rather go out of business than be part of Harvard. Two, the Supreme Court of Massachusetts said Harvard couldn't use the Gordon McKay funds for the thing. And what was the third reason? Can't think of the third reason right now. In any case, they decided not to merge, but between 1914 and 1917, they actually did merge the faculty. So Comfort Avery Adams was an MIT faculty member from 1914 to 1917 because they merged the engineering faculty at the two schools for those 3 years. It turns out in 1920, after World War II, Comfort Adams decided that welding was an important thing, and he started the American Welding Society in 1921. And he was the first president of the American Welding Society. Really high quality welds on a critical structure were not used until, with with shielded metal arc, were not used until the 1930s, and they built a 30-inch gas pipeline from Texas to New Jersey called the Big Inch pipeline. It was a 30-inch gas pipeline. And if a gas pipeline goes, you don't have flames 4 or 5, like in a acetylene tank, 4 or 5 feet or 10 feet in the air. The one in Edison, New Jersey, went a few years ago and had flames 600 feet in the air. Okay? Very exciting when you have a 42-inch pipe with 900 psi gas shooting out a flame. No one got hurt, although they claim a woman 3 miles away who had a heart attack that night died because of the noise. She was 80-some years old, but nonetheless, they claim that as the one fatality from the explosion. But in any case, that was when people started believing that welding could be used for critical structures. And then during World War II, they had to build ships again, only now they were building battleships with 17-inch thick armor plate. Well, you can't rivet 17-inch thick plates together. You got to overlap two 17-inch plates. How much overlap do you need to give them full strength, right? It's longer than the length of the plate. Plus, how'd you like to have to drive those rivets? In any case, welding kind of came into its own for critical structures during World War II for building ships. And I guess that's enough for today. Thanks. I'll see you tomorrow. We'll talk about arcs.